After we have seen in the previous lecture the discretized continuous time kinematic motion models, second order and third order, we are going to now take a look at another class of models, similar, but in this case we define the models directly in discrete time as follows. The discrete time process noise, V, will be a scalar valued zero mean white sequence. So that's a definition directly in discrete time. Variance is sigma v square, and you see here the Kronecker delta indicating the whiteness. And it will be, again, zero mean as before. So it is defined as a sequence. And the way it enters into the dynamic equation is according to the standard linear equation, xk plus 1 is fxk plus gamma vk, where we have now a noise gain gamma, which is an nx dimensional vector, and this vk is a scalar. The assumption, the physical assumption in the second order model is that the object undergoes a constant acceleration during each sampling interval of length cap t. So what we have is a constant value of the acceleration, and these accelerations, Vk, is a constant during kt, the interval starting at kt and ending at k plus 1t, and we indicate here a semi-open interval, which means the left end of the interval is already included in it and the right end is excluded. So that's called a semi-open or semi-closed interval. And the second assumption is that these accelerations are uncorrelated from period to period. In other words, we are talking about the piecewise constant acceleration. So this is what our equation, that the continuous time noise, which is acceleration, is a constant during one sampling interval, and it can jump to a new independent value in the next sampling interval and stays constant within the interval. So that's the piecewise constant assumption. An important remark about this model is as follows. It is clear that if the above assumption is correct for a given sampling period, t1, it cannot be correct for any other t2 except if t2 is an integer multiple of t1. Now, so we already see a physical problem here, but neither this piecewise constant white noise assumption nor the continuous time white noise assumption are realistic. Both are really approximations. The uncertainty in the motion, it's not going to be a piecewise constant jumping acceleration white sequence. It's not going to be a continuous time white noise. It's not going to be an autocorrelated random process either. So what we do in this case is make an engineering approximation that what we don't know is modeled as a random process, and we have several options. In most cases, we can find one of these options fitting reasonably well, but never perfectly, the reality. And this is going to be one of the things we'll see later when we model the motion of an object and we look at the results using those consistency tests in the from the Kalman filter chapter, previous chapter. And we'll find out that we cannot meet them exactly because the statistical assumptions are not satisfied. Nevertheless, this is about as close as one can get to the reality when you don't know the real thing. And therefore, these models have been in extensive use and quite successful. So, with judicious choices of the intensities, in spite of the fact that both these assumptions, as well as others that can be found, are really approximations, these, as well as others, can and have been successfully used as models for motion uncertainties, over short to moderate intervals of time. Another issue is over what intervals of time these models are reasonably valid. They are never exactly valid, that's clear. So this is why it is important to understand the underlying assumptions, their connection with the physical reality, and then judiciously select both the intervals over which such assumptions will be assumed to hold, as well as the statistical characterizations of these uncertainties, the noise variances. The discrete white noise acceleration model assumes that Vk is a constant acceleration during the kth sampling period. The length of this interval is cap t. Then the increment in the velocity during this period will be Vk times t, the interval, while the effect of this constant acceleration on the position is Vk t squared over 2. So what we have is, based on this, the constant gamma, which is a matrix, the noise gain term. Second element of it will be t, first element of it will be t squared over 2. Now, the state equation for the piecewise constant white acceleration model, or discrete white noise acceleration, we use DWNA, discrete white noise acceleration, as the designation of this model, which is of second order because you assume process noise acceleration, the states will be position and velocity, are given by, as before, xk plus 1 is fxk plus gamma vk, where vk is a zero mean white acceleration sequence. The transition matrix F is this 1t, 0, 1, it's a double integrator. New velocity is previous velocity plus the noise. New position is previous position plus t multiplying the velocity during or at the beginning of the interval plus the acceleration effect to the position, that's at squared over 2. So it is the t squared over 2 multiplying the process noise within that interval. Here's gamma, half t squared and t. The covariance of the process noise multiplied by the gain gamma, so that's the gamma vk, expected value gamma vk, vk gamma prime. V is a scalar, gamma is a 2 vector, so this is gamma sigma v squared gamma transpose, ends up to be a matrix that multiplies sigma v squared, the variance of v, where into the acceleration it is multiplied by t squared, into position t to the fourth over 4. You might want to take a look and see the difference between this and the similar expression of Q in the discretized continuous white noise situation. There we have a constant here, that's a Q tilde, the power spectral density, multiplied by T here and the T cube over 3 here. So the behavior in time of this, what amounts to integrated white noise acceleration into velocity and position, is different than what we get if we assume the piecewise constant white noise. Since the dimension of Q tilde was length square over time to the power 3, it's important to designate here that what we have now is the physical dimension of V, the process noise is acceleration, and sigma V, its standard deviation, are both length over time square. So clearly this is acceleration. This is one of the advantages of this model, that you get a little bit better physical intuition about it. When you choose an acceleration, the process noise standard deviation clearly will be of the same dimension, so you can talk about physical properties of the object motion. So, based on this, the guideline for choosing the process noise variance would be similar to what we had before, namely sigma v should be of the order of the maximum acceleration magnitude a sub m, and the practical range would be sigma v between half am and am. A so-called nearly constant velocity model is obtained by the choice of a small intensity, in this case the sigma v square, that's the q, in the following sense. The changes in the velocity over one sampling interval are of the order of sigma vt. They have to be compared and found small with respect to the actual velocity. So again, a relatively small fraction, 5%, 1%, 5%, 10%, that can be said it's nearly constant velocity. Again, in the literature, instead of NCV, you can find extensively the term CV model, even though it's definitely not constant velocity because there is a noise there. In the multidimensional case, with the motion in several coordinates with decoupled filtering across coordinates, our process noise really is block diagonal, and what we have seen before is one block of the overall process noise covariance matrix. So this is the decoupling of the process noise. It is assumed independent. Again, this is a simplification, but for linear models, it is hard to come up with a coupling across coordinates because sometimes it can be positive correlation, sometimes negative correlation. So the typical way such filters are designed is assuming uncorrelatedness among the process noise components in different coordinates. There is a third order model which says that it is not the acceleration that is a white process, but now the jerk is a white noise process, so the acceleration will be a Wiener process, the integral of the jerk. So this takes us to the discrete Wiener process acceleration model. For the piecewise constant Wiener process acceleration model, or discrete Wiener process acceleration model, DWPA, we have a third order state equation with components position, velocity, and acceleration. Again, the equation in matrix form looks exactly the same as before. Xk plus 1 is fxk plus gamma vk, but now x will be a three-dimensional vector. The transition matrix of this system reflects the fact that it is a triple integrator, and what we have here is gamma will multiply a process noise which is more conveniently defined as the increment in the acceleration. So you look at this equation, the acceleration, the third component of x at time k plus 1 is the acceleration at the previous time k plus the process noise. So the process noise physical dimension in this setup is still acceleration, but it is acceleration increment over a sampling interval. So we can summarize this, that the white process noise Vk is the acceleration increment during the kth sampling period, and it is assumed to be zero mean white sequence. Namely, the acceleration is a discrete time Wiener process. And the formulation in terms of acceleration is more convenient than the one in terms of the third order derivative, the jerk, because we have a better physical intuition when it comes to the acceleration an object can undergo. The covariance of the process noise multiplied by the gain gamma is Q, again, gamma sigma v squared, so this is the process noise variance, times gamma transpose, ends up with the matrix multiplying sigma v squared, where this acceleration increment variance goes directly with multiplier 1 into the acceleration, and would tick to the fourth over 4 into position. Now, the choice of the process noise variance. The standard deviation sigma v should be of the order of the magnitude of the maximum acceleration increment over a sampling period, delta am. And a practical range is sigma v between half and full value of delta am. Clearly, we said increment over a sampling period, so for different sampling periods, this model would need a rescaling of the variance of the process noise. To summarize the kinematic models, kinematic or polynomial models of order n state that the derivative of the position is equal to 0, this is the noiseless model, or is a white noise, that's the noisy model. And there are two major classes of noisy discrete time kinematic models. One is obtained from discretization of the continuous time model driven by continuous time white noise for a given sampling period. The other one is obtained by directly defining the process noise in discrete time as a sequence, and it is a piecewise constant white sequence. So the process noise is assumed to be constant over each sampling period, these are the pieces, and independent between or across periods, and this is the whiteness. And within each class, the following models were discussed in detail. The white noise acceleration model, that's a second order model, sometimes called CV, constant velocity, or NCV, nearly constant velocity. We have the Wiener process acceleration model, that's a third order in each coordinate. It's sometimes called CA or NCA, nearly constant acceleration or constant acceleration. The resulting process noise covariance matrices for the two classes of models are different in their dependence on the sampling period. So we talk about the two classes. One is the discretized continuous time, the other one is the direct discrete time. The process noise covariance matrices in the direct discrete time models are positive semi-definite of rank 1 because you have a scalar sigma v squared multiplying the dyad gamma gamma prime. The counterparts of this covariance for the discretized continuous time models are of full rank. However, both are approximations. Mathematically speaking, from the point of view of controllability of the state equation from the process noise, both have the controllability property satisfied. So the steady state solution of the Riccati equations are positive, definite, and unique, which is important in what we are going to see later because both these models lead to slightly different but fairly similar steady state explicit filters, which are known as the alpha beta and alpha beta gamma filters. Now, it's a little bit more common to use the model, which is the second one, the direct discrete time. The advantage of this one is that the process noise intensity is easier to relate to physical characteristics of the motion, namely acceleration. On the other hand, the model from item 1, this is the discretized continuous time model, is more convenient when one deals with variable sampling intervals. For fixed sampling intervals, probably doesn't matter much. When you have variable sampling intervals, the dependence on the sampling interval of the discretized continuous time white noise is a little bit more appealing. So we have two, there is no how to which one to use, and there are only guidelines as to how to select the parameters. Again, no hard rules there either. They cannot be because both are, as we discussed, approximations. Now, as I said, an important property of both of these models are that their corresponding Kalman filter Riccati equations do have a unique steady state positive definite, because first the observability condition from the position observation for the position velocity or position velocity acceleration state yields complete observability. It is enough to observe position for such states. Second, the process noise, as defined in both cases, ends up to yield the controllability condition satisfied. Therefore, Riccati equation is yielding in steady state a unique positive definite solution. So, if we have a state estimation problem for a time invariant system, namely the transition matrix is constant, the measurement matrix is a constant, we found the conditions, indicated the conditions under which the steady state covariance will converge and will give a unique steady state solution. Now, these conditions are satisfied for both types of models described before. What is also interesting, we can find explicit expression of the steady state covariance and filter gain in this case. So it is not only that we have a steady state, it's extremely easy to implement the steady state in view of the fact that you have explicit expressions for the filter gains. These are going to be obtained next. Okay, the problem that we have is either a two-dimensional state or a three-dimensional state, with Z being a position observation equal to hx plus w. That's a scalar. When the model is the second order model, h is 1, 0 to pick up position. When the third order model is the one that we are dealing with, namely the Wiener process acceleration, again it's 1 in the first location, 0, 0, we don't pick up the velocity and the acceleration. And the measurement noise autocorrelation function, EWK, Wj is an R delta Kj or sigma W squared delta Kj. We'll use the notation sigma W squared because it's a little bit more convenient. We'll actually need a square root of it, which will be easy, sigma W. But these are the same. Now, the resulting steady state filters for these noisy kinematic models are known as alpha beta and alpha beta gamma filters. For the second order model, that's white noise acceleration, third order model, that's Wiener process acceleration, respectively. The coefficients alpha, beta, and in the second case gamma yield the filter steady state gain vector components. You can find them in the literature under slightly different names. They really date back from about the mid-50s, so they are quite middle-aged, we can say, these days. Nevertheless, having been in use a lot during the times when computing was still expensive and was not available, fast computers were not available for real time. It is not the reason today to gain understanding that they are simple. The reason today to gain understanding is how the design of filters have to be carried out. And these models provide a tremendous insight into the design of filters for real systems. Okay, how we are going to derive the alpha beta filter? Again, it will be the steady state filter for a two-dimensional kinematic model, that's white noise acceleration. Plant equation is the xk plus 1 plus fxk plus vk, which must be very familiar by now. F is a double integration transition matrix 1t and 0, 1, and the process noise covariance matrix is Q delta Kj, so that's the autocorrelation really. and the measurements will be given by these equations with the measurement noise variance sigma w square. That's, we will not use the notation R, but sigma w square. Okay, what we will have as our goal will be the components of the steady state estimation current estimate or updated state estimate covariance matrix. The pkk, as k goes to infinity, will go to a unique steady state, and these components of the resulting steady state covariance matrix will be noted as Pij. So there are three such components. It's either 2 by 2 matrix, but symmetric, so there are only three. We will have a one-step prediction covariance, the pk plus 1k, same thing as pk given k minus 1. As k goes to infinity, its elements will be denoted by mij. And again, there are three of them. So now there are six. For the gain, the wk is denoted with component as g1 and g2. It's a column vector, so we have a transposition here. But remember, the observation is a measurement. When you update the observation is a position measurement. When you update with a position component, you will use a dimensionless quantity, which now we denote it as alpha. So the g1 is alpha. When you update a velocity component with a position measurement, you need a quantity that has dimension 1 over time. So it would be a scalar beta to be determined, dimensionless, divided by t. So alpha and beta are dimensionless, and the real gain is alpha and beta over t in column vector form. But the two numbers we need will be the dimensionless alpha and beta. So there are 8 unknowns in this case. As indicated before, existence, uniqueness, positive definiteness of the steady state covariances are guaranteed because the required observability and controllability conditions are satisfied. Okay, some of the derivations can be done in common for the two types, the discretized continuous time and the direct discrete time. The first phase will be carried out now. The next phase, where we have to separate for the two basic models, the derivations, because the result will be slightly different, will be carried out in the next lecture. So at this point, by looking at the gain equations, they can be expressed, gain 1, G1, in terms of the state prediction covariance matrix. This is the PH transpose over, there's the S inverse here. You have the state prediction multiplied by 1 because we make position measurements directly, plus the measurement noise variance. So this is the position gain, and this will be the velocity gain, G2. And again, it can be immediately replaced in terms of G1 and these two M's here. Now, the covariance update equation, that is P matrix, there are three elements here, the P12 and the P21 again has been denoted as P12, is I minus WH, and W has components G1, G2, times the one-step prediction covariance matrix. Again, there are three M's here, M12, and here we have the same thing, M12. So this is the state covariance update equation, and we have a covariance prediction equation. That's important. We have to relate it or write it backwards. We will multiply by F inverse, the pk plus 1k minus q, and then F inverse transpose to get the pkk. This is the way to eliminate some of the terms in the final equations. Now remember, F is a double integration. In discrete time, it has two unity terms on the diagonal. It's in an upper diagonal matrix, so clearly it has the two unity eigenvalues, so there's no inversion problem. F is invertible. And here is the expression of F inverse. The two eigenvalues are here. This is like, instead of propagating one step forward, this is the equivalent of propagating one step backward. Then the steady state solution for the covariance and gains is obtained from a set of fairly simple algebraic nonlinear equations using the expression of the process noise covariance Q. And here we have two versions, and that's why the derivation will have to be broken down into two, because the direct discrete time model Q is in 6324, while the discretized continuous time models Q is in 62212.